But if we do bivariate prediction, bivariate, bi meaning two, variate meaning variables, two variables, prediction lets us use the information from a correlational relationship to predict a score for the y variable based on the x variable. And that uses this process we call regression. I'm going to give you some language terms, little definitions about why these terms are used a little bit later. And so, for example, let's imagine we have a correlation. You might remember this from Psych 213 because this was one of the problems we used. Anxiety correlates with manual dexterity at minus 0.82. So as your anxiety increases, your manual dexterity, your ability to do small detail work, that decreases. So if we use this formula, we can predict people's dexterity from their anxiety. We can have a formula. We might find out, in fact, I created the formula, and so these are data based on that sample. If anxiety equals 2, we can predict for an individual that their dexterity might be 6.9. It's not going to be exact, but we can get a ballpark of where they're going to be with their dexterity. They're going to be pretty high. If their anxiety is 6, we can predict for any individual that their dexterity might be around 3.6. Likewise, if this is another one that we used, I think this year, I don't know if you took my 213, I'm not sure if you know this one, but if sunlight correlates with energy at R equals 0.81, that means as exposure to sunlight increases, then your energy level increases. So let's say this is the correlation. We can use this to create a formula. And so that if sunlight equals 10, then manual dexterity, energy equals 7.3. If sunlight equals 19, then energy might be 14.6. Excuse me one second. Okay, so that's how it's used. All right, that's what we can do with correlation is we can make these predictions. So some reasons, and these are reasons that are used. We could use individual students' high school grade point average to predict their likely college grade point average. And that means for an individual student. It's not going to be spot on, but at least we have an idea based on other students of what to expect. We do have to gather the data and calculate the formula. We could use the number of minutes of walking a person does in a day to predict the quality of their sleep that night. We could use an individual's income to predict their level of political influence. Just through correlational data, just by knowing each score for each person, then we can predict that for other individuals. We could use the amount of carbohydrates consumed in a month to predict the likelihood of developing type 2 diabetes. Maybe if we had a correlation. So this is how the data are used. Does that make sense, guys? Okay. You might think of others. We won't take that time now. So some differences. So when we're doing a correlation, we sort of can predict one from the other, but we're just ballparking. Like we could say, well, as sunlight increases, energy will increase, So that's sort of a loose prediction. But we also know it could go in either direction. Well, I don't think that one could go in either direction. I don't think if I have more energy, the sunlight is going to increase. But for a lot of correlations, they can go in either direction, or there can be that third variable effect. So in prediction, we have to do things a little differently. First off, we do have to establish which variable is which. And our predictor variable is always on the x-axis, on that horizontal axis. And the range has to be indicated because this is a visual thing we can do. And then the criterion variable, that just means what it is we're predicting. That's got to go on the y-axis. And then if we're using prediction, we're going to calculate the coefficients using raw scores instead of z-scores. And the reason for that is when we use z-scores, remember z-scores are standardized, and we'll talk more about that. But if I'm a college administrator and I want to predict someone's GPA, I want to know what their GPA is going to be, not what their z-score is going to be. And so it makes it more meaningful if we use raw scores for the person who's using the prediction. I wanted to talk to you about the language. These things always drive me crazy. And when I was in my stats classes, people couldn't really explain it, but words that I don't understand really bug me. So this word coefficient, we're going to see this. We saw that in our coefficient. We're going to see this a lot when we talk about regression formulas. And it stems from this word, that's a Latin word, coefficiens, meaning cooperating to produce a result. That's what the word means. And so when we think about a coefficient, we're just thinking about a number that cooperates with another number to produce a result. Maybe the number is multiplied by the other number, or divided, but that's all that means. So we're going to see that word in class a lot. So it just means a number that cooperates with another number. And then this word regression is what we're doing. We are using a formula to predict an outcome, but the statistical process is called regression. And this word also stems from a Latin word that means to go back. So you might hear, maybe you've heard already, or you might in the future hear people talk about regression to the mean. And that just means that like an extreme score is likely to go back to a less extreme score in the future. A team that wins all of its games in one season will not likely win all of its games in subsequent seasons. They're going to go down again. And that's the way things are. There's a regression to the mean effect that happens with data with all of us. And when we talk about this in statistics, it means that we're taking an outcome, like from our first example, manual dexterity, that's an outcome. And then we're going back to the factor or factors that contribute to it. I changed my example, but only changed it in one place. All right, so some language. A little bit more on this lecture, and then we'll get into a spreadsheet. So what we do is we create a rule. It's a linear prediction rule because it relies on having two variables that are related in a linear way. We can't have a curvilinear data. And so imagine this situation. After college, you get hired at a great university and you're the admissions officer. You have to figure out who to admit, and you have 200 students. That's what you have room for. And you have 1,000 applicants. How are you going to choose the students? And let's assume it's always beneficial for a college to choose the students who are likely to persist, likely to get good grades, likely to graduate. That's who you want to choose, because that's just better for everyone. And so you do have data. The students are all required to take the SAT exam. And you know that students who had scores of 580 had an average GPA of 2.62. Students with SAT scores of 590 had average GPAs of 2.66, and so on. So this is what you might be thinking. Could you use these data to predict what GPA an applicant with SAT 590 would achieve? Could you create a formula so that when you get new applications, you could enter their SAT score in a formula and use it to predict their GPA? And could you use that information to help you decide what students to admit? And if you think of this as a made-up scenario, it's not. All of these are algorithms that colleges, at least universities, definitely use to admit students. They're more complicated, not just one variable. In fact, all that uproar about DEI, not being able to include race, that means in their algorithm to predict the likelihood of succeeding or whether they should be admitted, they can't include race. So that's kind of what that was all about. They have to take that out of their model. So we make a rule. We will do this in real life in just a minute here. So what we do, just to give you some of the language though, we predict a person's score on Y by starting with a baseline number. And we call that baseline number A. And that looks like an alpha to me, but it actually isn't. It's just an italicized A. Whoops, let's get an A in there, not a U. So we start with that baseline number and we add it to the weighted score on the predictor variable. So we just take some weight and multiply it times whatever X was. In the case we just gave, we would be taking their SAT score and multiplying it times this weight and adding it to this baseline number. What we're going to calculate today are these baseline numbers and the weight. And so these are some of the language or symbols we'll be using. A corresponds with this baseline number. We call it a constant. And I'll talk to you about it a little more. But in this example, let's imagine that the constant is this 0.3. I'm just going to fade these in here. There we go. All right. So A is that baseline number. And in this example, it's been calculated and it's 0.3. B is the weight, and this is that coefficient we were talking about. So we have a constant and a coefficient, and that has been calculated, and it's 0.004. X, we know X, that's just the person's predictor score. In this case, it's the SAT score. And let's say the example we're going to use, someone got a 600 on their SAT. And Y is what we're trying to predict. And when we predict it, we put this little hat on top of it. We refer to it as Y hat. It's this little symbol on top, and that just means that this isn't the actual Y. This is just what we're predicting with our model. And this symbol on top always means like an estimated or predicted value. And so this is what the formula would look like for this example. We have a student who applied, they got a 600. We already know our coefficient B. We already know our constant A. And so the formula to predict their college GPA is A plus B times their score. And if we fill in the numbers, well, A is 0.3. And we add to it this 0.004 times 600. And that gives us, in the end, a 2.7. So that is our predicted score for our person, and maybe that helps the admissions officer. Does this make sense? All right.
Dr. S, I had a question. For the weight, I think it was 2 chapters ago, we had like weighted EVAR. Um, what does weight mean or like, like,
Um,
because I know it, like I said, you had weighted EVAR and stuff like that. What does that mean in terms of
yeah.
statistics?
So it means like how important that factor is. So going back to chapter 8 and chapter 9, when we were using those weights, well, we know that, let's just imagine a totally different scenario. Let's imagine that you want to find out how much people like the dorms or something. And you have responses from two separate groups of people. And one of those groups has just 10 people in it. And the other group has like 80 people in it. Well, which one do you think carries more weight or gives you more information about your dorm preference? Well, the larger group. You just have more information from that group. So you attach a weight to it that represents how much more information it has.
Okay.
Now, this weight, specifically called B, and it's used, this is not something for this class, this is the common word for it. It just means that for each, I have it written in a subsequent slide, but it means that for each 1 unit increase in X, how much does Y increase? So in this example, it means that for each 1 unit increase in someone's SAT score, how much does their GPA increase? Well, not very much, because you know that SAT has really big scores, right? So we looked at scores 580, 590, 600, but this narrows it down to just 1. And that's why this weight is so small. Now, when you're just doing bivariate prediction, which means you're predicting one variable from another, these weights, like, they aren't as meaningful as when you have multiple predictors. Because when you have many predictors, which we come to later in this chapter, then we might have, let's say we include high school GPA and SAT. Well, which one is more important in predicting college GPA? That's what the formula would tell us, and it would give us a weight for each of those factors, so we would know which is the most important for predicting your college GPA. Does that help?
Okay.
Okay.
Yeah.
Guys, my dogs treed this kitten last night, and I had been tending it, and one of them bit this kitten. One of this dogs just came to me, and it's raining outside now, and I don't think I can leave them out in the rain, so I have to just step away and let them in. I do apologize for that. Let me see if they have shelter.
Crystal, do you have cognitive psychology as well?
Yeah.
Did
Did you
you
get
finish
your paper?
I just got it back from proofreading.
Oh, really? I know I'm almost done with it and I'm turning it in today. I emailed the professor and he was like, "Okay, just thank you for letting me know." I was like, "Yeah." I know it's like all last minute.
Good luck with
Uh,
them.
Professor, I had to leave in like 5 minutes because I have to leave by 1 to pick up my son, and it takes us 20 minutes to get to the school.
All right, you'll want to watch everything. I'll record it and try and chop it up so that you know where should start. If I have time, I'll do that. Okay?
All right, thank you.
Yep. So this linear prediction rule, once again, regression is just another name for prediction. Regression is the statistical process. Prediction is what we use it for. A is the constant, and it's also the y-intercept. So when we look at later a scatter plot, it's the point where the line of best fit, what we call the regression line, crosses the y-axis. Now, in the past, for our regression lines, all we've been doing is kind of eyeballing it and seeing where we think this line should go, which is just fine. But we're actually today going to calculate it, this regression line. And so the point then, when we draw that line, the point where it crosses the y-axis, that's always going to be the constant. And it's called a constant because it's always the same. We always have to add it to the equation to get a sensible prediction for y. Okay, so that's more about A. B is this weight. We just talked about it. It's also the regression coefficient. By the way, in some places, they use different terms. They use B1. Let me see if this is all right. Oh, no. They use B1 for this regression coefficient and B0 for the constant. But I think more commonly I've seen it as A and B. There's always different language though, so just when you see it, if you don't get scared away by that. So B cooperates with or is multiplied by the predictor score X, and it also represents the slope of the line of best fit. It tells us exactly how much Y increases for every 1 unit on X. And of course, Y hat, that just means that we're predicting a value for Y, but we don't know for sure. Okay. And we could do this. We could plug in. In fact, we could plug in your data. How many hours of sleep did you get last night? Either anyone who wants to throw some data in for us.
6 hours.
All right. And what's your mood from a score of 0 to 8?
0 to 8. 0
Yeah.
being unhappy. I would say I'm a 5.
All right. You're kind of in the middle right now. Let's write those down. So we have X equals 6, and we have Y equals, what did you say, 5?
Yeah.
All right. And so we're going to plug this in a little bit and see how close your score is to this predictive model. For this model, we know that our constant, the place where the regression line crosses the y-axis, is -3. And we know that the weight, the coefficient, is 1. And X is the hours of sleep. We know Y, and we're trying to find Y hat. And so we can do it really easily right here. Let's see if we can just do it by hand. So Y hat equals A plus BX. All right. And so in this case, what would this model predict for you? We would have to take our -3 and add it to 1 times 6. And so -3 plus 6 equals 3. So they predict a 3 for you in terms of your mood based on this model. Your actual score is a 5. The difference between these scores is called the error. Or sometimes it's called the residual, just so you see both of these terms. If you Google something, error is the same as residual. And we just define it as Y minus Y hat. Of course, we'd figure it out for the whole database, not just for one person, but that's called the error. The model can't be perfect, right? And in this case, it was off by 2. So that's the error. So if a person got 8 hours of sleep, the model would predict 5. If the person got 6 hours sleep, the model would predict 3, as we know. We do have to set ranges. We couldn't have someone getting 18 hours of sleep and get a reasonable outcome, because that would probably mean they're really sick or something like that. So we'd have to set some ranges that the model would work for, but that's how it works. Now, this regression line is what we're going to start with. And so when we get into our spreadsheet, so it is just that line of best fit. And in the past, you remember, we were just kind of eyeballing it and figuring out where it is closest. Well, we can actually use a formula to get the line that's closest to the most number of variables. And so, first of all, the x-axis is for the predictor variable. It begins at 0, or it begins at the lowest point in the possible range, is a more sensible way of saying it. If 0 isn't a possibility, it doesn't begin at 0. It begins at the lowest point in that range. The slope, that's how much the line moves up for every unit it moves across. How much does y increase for every 1 unit of x? And then the intercept, or the constant, so here we have more words here, b is still the regression coefficient. That's still true. I can't write on the screen. And it is, let's see, it's also the weight. So we've called it all these different words. B kind of means all of those things. And then the intercept A, that's the constant. That's what we're always adding. And then the error term that we use when we're calculating if it's the best model is these differences, right? But we're always squaring these differences. So we're taking these differences and we're squaring them. So it's y minus y hat squared. And then we're figuring out the line that has the lowest squared errors. This right here, this regression line, this is like the predicted values. This is the y hat predicted value for each score. And so the difference between each person's score and their predicted score, which would be here, that's the error. And we want to have the line drawn that has the least possible squared error. And so when we square it, we're making sure that those extreme values are really indicated strongly. So that's why we always square. That's one reason we always square. So we conceptualize it then, looking at the very same video, we conceptualize it then, the model we're using is called the least squared errors. And that again just means all of these error terms right here, these differences between y and predicted y, squared. Sum all those up. What's the line that makes the smallest value there? And that's the appropriate regression line that we use to represent B in our model. And so then here are the formulas. So B, we'll use these in the model in a moment, is the sum of x minus mx. Now, you already calculated this. Each score minus the mean, that's just our deviation score. When you run a correlation, you calculated your deviation for scores as your very first step. So you already have those. And we subtract it, we multiply it by the other deviation score. So we could say deviation times deviation. And we divide it by the sum of squares for x. That's it. To calculate A, the constant, we take the mean for y, and we subtract that B that we just calculated times the mean for x. That gives us the figures we use to do two things. It gives us the figures we need to predict a score, and it gives us the figures we need to draw the regression line. We draw the regression line. Once we do that, we only need 2 points. So let me see if I actually have a scatter plot in here. Let's see here. I don't actually have a scatter plot, but let's say these were our data distribution. Well, what we would do is we would use these numbers that we calculate, and then we would choose one kind of score anywhere on the x-axis. We'd say like, a score of 100. What is y? What is y if x is 100 using the formula? We calculate it and we plot the point. In this case, that score was right here, around that 1.5 mark. And then we do that for another point. So we do that for one score, and then we do it again to get one more score. And once we have 2 scores, let's say we choose 200, and we use our model, and we find out that the 200 score is right here. Well, that's it. That's all we need. We can predict. Now we know what our line of best fit is. And we know what our y-intercept is because it's got to be right here where that line crosses the y-axis. Remember, the y-axis can continue into the negative numbers. It may cross it way down here somewhere in a negative range. But this is the y-intercept, or A, in our model. And this is the slope for each unit on x. How much does y increase? That is our beta. All this is just conceptual. A little bit more conceptual we're going to go through before we get into our first problem. Any questions right now?
I think it'll start to make sense when we do a problem.
Absolutely, it will. So this is just giving you an overview. And so then once we work with it, it'll make a lot of sense, actually. I'm just going over this first, though, because that is a good starting point. We already talked about that. Now, all of this that we've done is unstandardized. And so let's just review what we mean by standardized and unstandardized. So standardized means that the scale is the same regardless. It's not. Hang on, let me see if I have unstandardized. Okay, so unstandardized is just our raw scores, right? In whatever it is. So just to go back to a really basic level, if I'm trying to measure my room and figure out how much carpeting I need, maybe I don't have the appropriate tool. I don't have a yardstick. And so I just go walk toe to toe to toe to toe to toe. And I say, okay, my room has dimensions of, you know, Suzanne's footprint, times 10, like that. That's unstandardized. Of course, I can't make any decent use of that information when I go to the store. I had better figure out exactly how long my feet are in a standardized measure because that's allows us to communicate. And so we also have a standardized correlation coefficient. So the standardized just means the scale stays the same regardless of the units of measurement in the original scale. If I measured my rug in feet like I just described, like my footprint, I've got to standardize it in order to buy my carpet. Things like miles, pounds, inches, all those are standard measurements. And of course, in our statistics, our z-scores were standardized measurements. Our t-scores were standardized measurements. Standard deviation is a standardized measurement. It just makes sense regardless of the scale of the original data, regardless of whether I used my footprints or actual foot ruler, something like that. And standardize is helpful in a lot of ways. Like if I want to look up all the studies that are linking, SAT scores with GPA, well, that's not a good one, that are looking at predictive test scores with GPA, well, all those tests might have different scales and the answer won't make any sense to me unless they're standardized, then I can compare them. So here is an example that I was just giving. So there are two really big exams that high school students take if they want to go to a university for their freshman year of college. One might be the ACT exam. I know in Wisconsin, where I grew up, that was the more common exam to take, and maybe across the Midwest there. And the SAT exam is an exam that I know was taken more in the East Coast. And both of these are accepted by universities. But the ACT produces scores ranging from 1 to 36, and the SAT has scores ranging from 400 to 1600. And so looking at someone's raw score on these doesn't mean anything. We have to standardize them and look at what their z-scores would be. And if we find a correlation, if we're predicting one score from the other, we have to standardize it in order, which we did in our own class. We have to get a standardized score as well. So that's just a little bit about that difference. And there is a formula for it, and let's look at some symbols. So B that we've looked at, we called it the slope. We called it, what else did we call it? The regression coefficient. What else did we call it? I think that might be all. The weight, we called it the weight. All of those are true. It's also the unstandardized coefficient. It relates to the raw data and it uses just this letter B. And that's what we call it, B. And it's typically italicized. But if we have this Greek letter beta, that is a standardized coefficient. And so that's analogous to our z-score or our t-score. It's standardized. Everyone knows what it means. It does have a formula. It's just the b that we calculated times square root of ssx divided by the square root of ssy. All right. So that's just a little bit about the standardized. We're almost to the end of this section here. A little bit more facts to throw at you, and I will put these slides up. We also want to know how good the predictive model is. How much of the variance is it explaining? If we're using SAT scores to predict college GPA, how much of the variance in GPA does it explain? Like if it explains like 1% of the variance, it's not a very useful predictor. If the SAT score explains like 70% of the variance in GPA, it's a really good predictor. And that's what we want to know. And we call it a predictive model because usually we have more than one predictor. But in our example right now, we're doing bivariate. And so we're just using that one predictor. Right? So just some terms here, and then we jump into our spreadsheet. So when we ask how good the model is, we're asking how much of the variability in Y is explained by X. Or to look at another way, how much error is in the model? How far away are those scores from that regression line? Because we want those scores to be close. And we look at three factors. I'll show you it here, and then I'm going to show you on the next slide in a formula. And I think that's the last before the summary and then the spreadsheet. So regression is the variance in X that's explained by Y. So it's just that distance. Remember when Cassandra got a score of 5 on her mood and her predicted score was 3, that difference is called error, and that's one of the things we consider. Let me see. No. I said it backwards. The regression line is actually the good thing. The amount of the variance in Y that is explained by X, and it's calculated by taking the predicted value of Y and subtracting the mean of Y, and we actually will calculate sum of squares, but that's what it means. Error is what I just described a moment ago, and that's what when Cassandra got a 5, but she was predicted to get a 3, that difference is the 2. We calculate that for all of the individuals, and then we know how much error there is in our equation. So it's Y minus Y hat, and we'll actually calculate the sum of squares for that. And another word, remember, I told you this word before, this is also called the residual, and some of our statistical packages use that word residual, sort of like the leftover, the leftover variance is another way to think about it. And then if we add those two together, we'll get the total variance, okay? And so that means we can do some little calculations. If we take total minus error, we get regression. If we take total minus regression, we get error, all of that kind of thing we can do. And these are the formulas. So proportionate reduction in error is how your book refers to it. I use the acronym PRE, but this is not a mathematical acronym. I just did it to save space. So it's just the proportion of the total error that our formula explains. Total variance, I guess, that our formula explains. How much error does our model reduce? Like, does our model tell us anything more than if we just, subtracted the mean? Are we getting any more information? Is our model useful? And we calculate it using these three, and this relates to these three ideas: total, error, and regression. So SST means SS total. And it's going to be exactly the same as the sum of squares we calculated for a correlation coefficient for Y. It's the sum of Y minus the mean for Y squared for each score. SSE is the sum of squares error. That's the distance between the regression line and each score. And that is the one that we talked about with Cassandra, having an actual mood of 5 and a predicted mood of 3. We square it for each individual and sum it up. We get SSE or SS error, sum of squares. And then SSR, or SS regression, is the distance between the predicted Y and the mean for Y. In other words, the sum of Y hat minus the mean for Y squared. And these are our three calculations. And then we take them, let me see. And the formula is right here. SS total minus SS error divided by SS total. And I think I have this here. So SS total is, we know this, is the sum of squares for regression plus the sum of squares for error. We know that. We know that this PRE is SS total minus SS error divided by SS total. But since we also know that SS total minus SS error is SS regression, we could shorten our formula to SS regression divided by SS total, and then we would get our proportionate reduction in error. And once we do our calculations, we're going to see a few things when we do these. But one thing we're going to see is that when we do all that calculating, we're going to get R squared from our original correlation. That's what this is going to come to, R squared. And so I told you in our last class that R squared is what we need to, how much of the variance in Y is explained by X. Well, R squared is the same thing as this calculation, and we'll see this in a moment. So R squared, I mentioned this to you last time, is the proportion of variance explained by the predictors. And I just put this asterisk here because I wanted you to know PRE is not a common mathematical acronym. That's just what is used in your textbook, and I wanted to be consistent with that when I was describing this to you. So to summarize this, and then we'll go into the spreadsheet. We can use data from an X variable to predict a score on a Y variable using this formula. We can calculate B and A from a data set and use it to create a well-fitted regression line based on this least squared errors principle, the line that has the shortest distance between itself and each of the scores, or between Y and Y hat. Prediction models rely on the unstandardized coefficient and constant so that the predicted score is sensible in terms of the original scaling. Standardized coefficient represented by beta allows score from many different scales to be interpreted sensibly. And the predictive